I don't know. Okay, so 2.6, proofs using segments. So we're doing a lot of proof stuff today. That's pretty much all you're going to have to like write down today is the proofs. All right, so first up, the Bible says that we are to work diligently at the task set before us. Genesis 2:15, Ephesians 4:28, Colossians 3:23, 2 Thessalonians 3:10 through 13. All of these reference that, okay, that we must be diligent and have perseverance to succeed. I think the reason the chapter starts with this, and like it has scripture in other places, but this was a good one to include because proofs are not easy. I know that, right? This is your first year of geometry, the only year, you can breathe, the only year you have to take geometry, right? But some people choose to study this, right? Um, so just remember to be diligent and to persevere, even though it's hard or difficult or you're not understanding. So some helpful steps to doing that. First is to identify the premise. Okay, that's the given information. Okay, also my board's been really glitchy lately, last week and this week. So hopefully it'll work. It didn't work in my class earlier today. So it's the given information. Okay, so identify the premise. And step 2, it says identify the conclusion. That's what you're trying to prove. And you can start proofs that way. You can put in the information you know and the information you have to find out at the beginning and the end, and then just fill in the middle. Right? You're going to fill in the blanks. Step 3, make a sketch to ensure you understand. I have done that for you on the notes today as well to kind of piece through some of the things. And so those are still there, the sketches. But don't be afraid to sketch something. It's tremendously helpful. Step 4, consider any related definitions, properties, postulates, theorems. Okay, all of those things can be included in your theorem when you're doing it, or in your proof, sorry. And step 5, work backward from the conclusion if necessary. Okay, these are all things that I hope to model for you, maybe not today, but as we're progressing through them. It's totally fine to be like, okay, well, I know I need to do this. Get this. Well, how do I get that from what I have? Like your brain kind of sometimes already knows it, but it's like, how do you explain it? Okay. Now, the type of proof that we're going to spend most of the time doing is a 2-column proof. All right, so a 2-column proof is the most common. That's why we're going to do it. And its statements are easily identified when written in that P, if P, then Q format. So what you need to know in a 2-column proof, we have the statement of the premise, the statement of the conclusion. Okay, we're going to have a diagram. So that sketch was what, number 3 up there. And then we're going to have columns because it's a 2-column for statements and reasons. Those are going to be in there. So if you want to draw that in, you can, but we're going to jump right to it. And then any equivalence relation, anytime you have an equivalence relation, it's going to exhibit either the reflexive, the symmetric, or the transitive properties. And those are the ones that we did in our warm-up this morning, or today. Okay, you wrote those. So remember again, what was the reflexive? A equals A is reflexive. What was the symmetric? Okay, if A equals B, then B equals A. All right, and what was the transitive? Okay, so if A equals B and B equals C, then A equals C. All right, those are those properties in some shorthand to help you remember, because sometimes that will be helpful. All right, so we're going to dive right into this first proof. You don't want to dive? Okay. I'm going to leave it here. I know it's kind of hard to see, but I'm going to leave it here for just a second to show you that it does have all these things up here. Okay, so it says, example 1, prove. A line and a point not on that line are contained in exactly one plane. So we need the statement of the premise. Okay, we said that was the same thing as given. So we wrote a given statement. I've written it for you. So there exists a line K and a point P not on that line. A lot of times these are given to you even, the given and the and what you need to prove. And then the statement of conclusion is where we have here, prove. There is exactly one plane, one plane of, is that what that says? Oh, one plane Q, sorry, one plane Q that containing Q and P. So there's that statement of conclusion. My diagram is over here. And then I set up my columns for my proof. So here's my column. My 2-column proof is here. There's the statements, and here's the reasons. So those are the 4 parts of a 2-column proof. All right, so let me clear all that out, and we'll actually do the proof then. Yay. All right, so let's look at that a little more in detail. So there exists a line K, which is labeled. Okay, that's what this is what they gave us. This is the sketch that I did to add to it a little bit. And a point P not on that line. And there is exactly one line, or exactly one plane Q containing K and P. All right, so what's the given information here? What's given? Because that's my first reason, is given.
So would it just be there just line with K?
Yeah, we just restate this. So there exists a line K and a point P not on that line. That's my given. That's what they told me.
You really had to do that.
Mm-hmm.
I had a little sphere thing that could roll around, and he flattened it.
I'm sorry. That's a bummer. So then also, right, so that was step 1. Identify the premise, the given information. Step 2 was identify the conclusion. We could go ahead and do that. It's kind of nice because I went ahead and gave you like 2, 3, 4, 5. So we know that this is the conclusion. But we could go ahead and write 5 in here if we wanted, because we know exactly what we need to prove. What are we proving?
There's exactly one containing K and P.
Okay, so this one I'm going to tell, we're not going to do that. I'm not going to write it down in those words yet, just a second. We could, but it's easier to do when it's more of like a mathematical phrase versus like Q equals 16 versus writing the whole sentence, because we might want to write it differently. But we still know that's what we're going for. All right, so here's the deal. On this one, we're kind of doing plug it. We're going to plug in the next step. We know we have to apply the expansion postulate. What is the expansion postulate? If you don't know, you need to go back and find it.
Expansion postulate is...
Find it in your notes.
The expansion postulate.
Wasn't it something to do with that you need 3 points on a line to have a plane, or 4 points into the plane? Or, I forgot what it was.
You are getting close.
Isn't that the one that there's 2 points on a line, 3 in the plane, and 4 in space?
Yes. Nice. Okay, so that expansion postulate is one of your incidence postulates. It's in section 1.3. Oh, you found it? Good. So read it. Okay, read it to what is this?
A line contains at least 2 points. A plane contains at least 3 non-collinear points. A space contains at least 4 non-collinear points.
Non-coplanar.
Non-coplanar.
Okay, fantastic. So that's in 1.3. So how is that going to apply to this? How are we going to use that here? We are. It says I am. Like I already gave you that. No. What's it say? So we're talking about a line, right? What does it say about a line? Expansion postulate says what about a line?
At least 2 points. You have 2 points.
I don't have 2 points. In my drawing I put them, but it wasn't in the original, right? I just had a line K and my point P out in space. But I did put these on here to help us. So we could fill that in a little bit.
There's going to be 2 points on it.
Okay, so we're going to, 2 is going to say a line contains 2 points. And so we could say X and Y. We need to name them because we, like we can reference them later. So that's what we added to our sketch. So that's our expansion postulate. Very nice. Okay. Where can we go from here, do you think?
Another postulate.
Maybe another postulate. So now I've got 2 points on my line and a third point. Does that help me with anything?
A planar. A plane.
A plane? Okay, what do we know? What do we know about X and Y?
Have to have 3 non-collinear points in a plane.
We have to have 3 non-collinear points in a plane. Yes! So X, Y, and P are non-collinear. That's perfect. So what's the reason for that, though?
Plane postulate.
The plane postulate. Let's see. That's not what I...
Non-collinear points in one plane.
3 non-collinear points lie in exactly. This is true, but you're calling it a plane. Right now I'm saying they're non-collinear. So you're close.
Flat plane postulate.
It's actually just a definition.
Plane. Definition of plane.
So this is a definition of
Plane.
not plane, non-collinear. Yeah. I think it has 2 L's in it, not 1. Yeah, so that's just the definition of non-collinear points, even. Sorry, non-collinear points I need to put on there. Which I can totally understand why you think is the plane postulate, but in the next, we need to say that those are, we haven't stated that those are a plane yet. So it's taking it literally step by grueling step is what proofs do. So we're saying, hey, X, Y, and P are non-collinear, which means what? That they make a plane. Okay, so X, Y, and P, okay, we can say make. Okay, make a plane. And so what is that? The plane postulate. Very good. Okay, so our last step is something about we're proving there's exactly one plane, Q, containing K and P. Oh, and we could say here too, X, Y, and P make a plane. We could name it plane Q. Well, because we want Q here. So that's a comma. It looks like a 1. X, Y, and P make a plane Q. So then what's 5 going to be?
Conclusion.
Okay. Do we want to write that whole thing? Or do you just want to say plane Q contains? Well, we don't need X, right? We just want to know that it contains K and P.
So plane P contains K and P.
Okay.
Plane Q.
Plane Q contains K and P. And what would that be? It's another postulate. Not a conclusion postulate. Good try. So back in that 1.3, those... Nope. You're just reading them all. It's not going to serve you. Why is it flat plane postulate? Because there's a line in it. Okay, so the flat plane postulate says if 2 points lie in a plane, then the line containing those 2 points lie in the same plane.
Yep.
So that one is the flat plane postulate. Okay, so who is like, this is horrible?
Yeah. Yeah. Because I still don't see any
There aren't any numbers in this one.
Except for number 1, 2, 3, 4, 5.
Right. But and that's the thing, there aren't any numbers. And again, that's why I included our scripture for the day, like to be diligent and to persevere. Because it's not easy, and I know that. But you have to give it your best. So one question in particular, do we understand that the numbers, like we're saying something and then we're giving the reason?
Yep.
Are we good with that? This is what we can conclude, and this is why we can conclude it.
I kind of thought that was just like the definition of it.
Yeah, it is the definition of it. Okay, so we're good with that? All right, then let's flip over to the back, and I feel like the next one is a little easier to follow, but I like segment congruence and stuff more. So here's our new theorem. Segment congruence is an equivalent relation or equivalence relation. So that's theorem 2.6.1. And our next proof. So prove the symmetric property of congruent segments. Okay, again, we have our given statement, we have our conclusion, we have a diagram, and then we need our two-column proof, like a T-chart. All right, so number one is what? Number one is always the what? The given. So they told us segment AB is congruent to segment CD. And what's our reason for that? It's given. That's the easiest one to do. Judging. 4, okay, so this was our proof. I did go ahead and just put it in there, right? That's what we have to prove this time. It's a little bit easier in these to write the conclusion exactly because it's not a whole sentence. All right, but then how do we go about solving for it? All right, so we have to look. It told us AB is congruent. Nope, you'll never measure. You'll never measure anything in like when it comes to this. Your measurements are worthless. So
that's like an instant given saying, oh yeah, they're congruent, measure them.
Yeah, but in geometry, we want to find why they're congruent, not besides measuring them, because people can measure incorrectly.
Okay, I know you've heard this before, but why would we need that in real life? Like explaining why.
So this is like logic, like looking at people's arguments and things, candidates when they're running for election or different things, or even advertisements, like if you do this, then you get this, and blah, 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 or a salesman calls you. Like it's looking at arguments and saying, like, are they truly valid? Does this logic line up? Yes, ma'am. Yes.
So it's like, right now it's just logic, it's not even like geometry.
Well, geometry and logic kind of go hand in hand. So let me help you out with the next one. On the next one, we're going to say, well, AB equals CD. Instead of saying segment AB is congruent, I say AB is equal to CD. Anybody know what that one is?
That would be... Bear with me there, bud.
I was trying to find.
Oh, no. Yeah, you forgot to tell me.
I'm sorry. Okay, Tori, are you okay? All right, so we're going to need all of our notes. We're digging through today. Remember, we can use definitions, we can use postulates, we can use any of those things.
Would it just be... Or would it be reflective? I don't know. Not gonna lie.
I think it is.
Symmetric?
It's not. This one is just the definition of congruent segments. It's a squeaky pen. So where are we going to go from here to get here? You switch around to be what? Because they are switched around here, right? We have segment CD is congruent to segment AB.
So I got this. Symmetric it?
We symmetric it. Sure.
That's a verb now.
I realized I picked up on that. So what does that mean to symmetric it?
CD equals AB.
Yeah, so we would say CD equals AB, which, since we symmetric it, that is the symmetric property of equality. So then what's the fourth property? Or what's the fourth one? When we go from... What was it when we did this one? When we took the segment lines away? The definition of congruent segments. And so now we put the segment lines back on. It's the same thing. Did somebody say they're lost?
I said, oh my gosh.
Oh, okay.
You might actually like geometry. There's no numbers. That makes it worse.
It's like sometimes they can make it worse. Okay. Okay, so then we say, okay, this is emphasizing the difference between sets of points which are congruent and their measures which are equal real numbers. Okay, so the definition of congruence is used to switch between congruent objects and equal measures. So that might be helpful for you to underline or highlight. Okay. So the definition of congruence is used to switch between congruent objects, okay, so like the segments, and their measures, because this is a segment, that's an object, my arrow, where this one is a measure. You can't read that at all, but it says measure. So that will be kind of helpful. Okay, let's try the next one and see what we can get on example 3. It's not clearing. Okay, there it goes. All right, so example 3, we're given segment LM is congruent to segment PQ, and we want to prove that segment LP is congruent to segment MQ. All right, so we just did some segment ones, and we used the definition of congruent segments, and look, it's showing up again here. So we're going to take that. Do you need to stand up? The hell? Do you need to go get a drink of water? Are you sure? Okay, no, don't do that. Okay, so Lucas, what's number 1?
It's just the LM equals PQ or segment.
Okay, so that's congruent, not equals.
Congruent.
Okay, so segment LM is congruent to PQ. Perfect, because it's that given. Awesome. Step 2. There's several. 7, to be exact. Okay, 7. It's telling us, I gave you that there's 7 total. You asked how many are there?
You went to 7 and it was confused for a second. But then I'm like,
Okay. Gotcha. You had asked how many there were, and I said 7. Okay, so on the next one, I told you it's the definition of congruent segments. So what's 2 going to be?
Is just LM equals PQ?
Yes. Just like we did. Perfect. So LM equals PQ, because we were talking about the length of the measure in one, or the object in one, and now we're actually talking about the measure of them. So perfect job. All right. So here's the thing what we're trying to prove. We've got our sketch up there. LM is congruent. We know LM is congruent to PQ, right? So LM is congruent to PQ. But we're trying to prove, okay, so I'm going to erase those. we're trying to prove that LP is congruent to MQ.
Yep, looks close enough.
Looks close enough, isn't good. So how are we going to do that?
Switch the P and the M.
Well, what's different about LM? Okay, so LM was from here to here. Whoops, dang it. Again, my board is really glitchy. I'm really sorry. It doesn't want to do any of the things that I tell it to do today.
It'd be the commutative property of multiplication.
Okay, so L to M is here, and then P to Q
No, wait, never mind.
is here. What's different? What changed?
The
But
M and the P's.
the M and the P. Okay, so let's do something with M and P. Like we could say MP equals MP.
What?
MP equals MP. What property is that?
Wouldn't that be like what was it called again?
Uh-huh, you know it.
It was
Symmetric.
Nope.
Or sorry, reflexive.
Yeah, reflex.
Yeah, this is the reflexive property. Again, it's of equality, so I'll put the equals on there. That's the reflexive property of equality. We want to establish that, hey, MP is equal to MP no matter which way you like, no matter what we do. They're equal. Okay? So now that we know that they're equal and we've said why MP is equal, what are we doing with this segment and MP?
Adding them.
Adding, oh my gosh, we're adding them. So we're going to say, we could say LM plus MP equals
LP.
LP.
Hey, I know that one. That's
Right? Like we're adding these two segments and we're getting this new segment LP.
Maybe an additional property of equality.
Let's see. Okay, and so we can actually put two of these, we could put two of these together.
be transitive.
Okay, hold on. It's not this one. What are you saying? It's the transitive property? This one's not the transitive property. But hold on. Because what are we doing?
What the transitive is showing.
Well, the transitive is showing
Oh, that's
when you actually multiply numbers. This one's not because it's actually changing it. Addition. This is the addition property.
You just said that.
I didn't hear you. I apologize, dear.
she has my headphones.
Yeah, I do have the headphones on, so sometimes I don't. So this is the addition property of equality. But we can go ahead and do both of them at this step. If LM plus MP equals LP, what about the other segment?
MP plus PQ equals MQ. Is that step 5?
Do what?
Is that step 5?
No, that's all step 4. Like we just can put them into the same one. All right. You guys are rocking it. All right, step 5.
Yeah, once you see your homework.
Oh, wait, hold on. Let's see. Let's see. We said this was the. Let me go back to the addition property. I actually had the addition property for step 5 and a different one for this one. Where did you have the addition property of equality? Yesterday? Addition property of equality. If A equals B, then A plus C equals B plus C. Yeah, see? Okay. This is, yeah, I would take addition property still, but I also have the definition of betweenness, or of between, as another one. Because if you were, I don't remember, when we talked about what between was, we added two segments so we know what that M is between L and P. And then MP plus PQ, P was between. So both of those, I would take either of those. Okay. All right, so where to now? Okay. I was like, it's LP equals MQ. Good. And how do you get that? I do not have symmetric. I just have substitution, the substitution property. Go figure that you had that too. Why did you think it was symmetric, Lucas?
They switched or two of them. I can see it be the
Okay, because yeah, with symmetric, we're saying that's if A equals B, then B equals A, right? So we still have the same order, but now we're substituting in what we just discovered, like MP equals, because we added MP to both, and so since MP was equal to MP, we can substitute LP for LM and MQ for PQ. So this one is just substitution. So we're actually going to get this done in 6 and not 7. We kind of skipped a step that I think is okay to skip. So
Won't you do the segment LP's segment NQ?
yes, we would. Segment LP is congruent to segment MQ. And what is the reason for that?
Conclusion.
Never is conclusion acceptable. Given, yes. Conclusion, no. What is the reason? Definition of congruent segments, right? We can go back and forth between that all the time. So the definition of congruent segments. Okay, so then on your own, you're not writing proofs for these.
Thank you.
Just what can you conclude and why? So that's essentially you're giving me a statement and the reason why. It's like one step of a proof that you're doing for each of those is you're just going to have one step of each proof.
Can you do the givens?
No. Good question. Can you do the given? Nope, it can't be given. It has to be why.